Hello and welcome to this video on Bronsted-Lowry acid-base reactions. So in this video I'll show you how we draw our conjugate acids or conjugate bases and indicate which side of the equilibrium is favored. Okay, so let's start off here. So we have in this molecule an oxygen bound to a potassium, but bound ionically. So what we can do here is we can move this potassium ion. Let's give it a plus because it's a cation. And this oxygen then has a negative formal charge because what is not being shown here is these lone pair of electrons. So if we place these here on the oxygen, let me move this charge a little bit higher so we can see this. Okay, since we have a negative formal charge on our molecule, this is going to be our base, because bases tend to be negatively charged, have a negative formal charge, or neutral. Plus, this doesn't even have a proton to donate, so that's obviously our base. And then this then would be our acid. What we like to do is use arrows to indicate where we are making bonds and where we are breaking bonds. We always start at our base. So we'll start at a lone pair right here, draw it towards our hydrogen. And what also is not being shown here is this hydrogen-nitrogen. For some reason why those are together. Let me do this so we can see it a lot clearer. So we have a nitrogen and we have a hydrogen. So nitrogen here and our hydrogen, which we will be taking and making our bond with our oxygen. But there is a bond right here. So we also have to indicate that we are breaking that bond and placing those lone pair onto that nitrogen. So let's redraw this molecule over here. And to save time, I can simply just do this. Copy and paste. There we go. So move this atom over here. I totally forgot a bond. Let me get this bond back. Okay. So here's our oxygen, and what did we do here? We ganged a proton. So we also need to show that we ganged a proton. So now this oxygen does not have a negative formal charge because it's negative over here. We're gaining a proton. So a negative plus a positive is a neutral. So there's that. Now we need to draw our acid. So let me just copy and paste this over here. Hopefully I don't lose any bonds anymore. So, oh, I got an arrow too. What do you know? Oh, we lost the bond too. Alright, so here's our other bond. And what did we do here? We lost our proton and we pushed electrons onto this nitrogen. So this nitrogen has lone pairs on it. Originally it had one lone pair right here, but now we have two lone pairs because we broke that bond between the hydrogen and the nitrogen. Whoops. There we go. So this nitrogen was previously neutral and it gained a lone pair. So a neutral plus a negative, because electrons are negatively charged, would cause this nitrogen to now be a negative. So let me just put a plus here to indicate our reaction. So what is our conjugate acid? Our conjugate acid is the molecule that gained the proton. So this is our conjugate acid. The molecule that lost the proton is our conjugate base. Okay, we are almost done here. All we have to do is indicate the side of equilibrium that is favored. And when we do that, we compare our conjugate base to our base. And we decide which one is more stable. The more stable compound will be the area where the reaction's favored. It'll make more sense when I show you. So this conjugate base has a negative formal charge on a nitrogen. It can't undergo resonance, and it's sp3 hybridized, whatever. This oxygen, or this base, has an oxygen with a negative formal charge, which is more electronegative, and it has a lone pair that can make resonance, so this obviously is going to be the more stable compound. So this is a more stable molecule or compound, whatever. We can draw our resonance arrow indicating that this side of the reaction is favored, and the reason being would be resonance, or you could say electronegativity,